So then I will have to discuss some variation. So today the plan is to discuss infinite version of pigeonhole principle. Okay, it's simple, just simple idea, the same idea, but just for a new name, infinite version of pigeonhole principle. Okay. So this can be said in various different levels. Okay, but we will do it just in the following way. Okay, if there are, and this is a visibly very obvious statement. Okay, can you guys guess the statement? What should be the statement? What should be the infinite version of pigeonhole principle? In any form, maybe you can say in terms of pigeons in cages. What should be the infinite version? Like you should have an idea of it first, right? But there is nothing. So infinite minus one, that's the problem with infinite minus one. Yeah, infinite minus one is again infinite. Yeah, so yeah, there's more technicalities in that, but infinite minus one we will not say. We will say that if there are infinitely many pigeons, it's impossible, but if there are infinitely many pigeons and finitely many cages, okay, yeah, so that is the next smallest. So the next smallest thing before infinity for us is finite. So there are many things in between and so on, but for us before infinity there is finite. Okay, like we know that before n plus 1 there is n and n minus 1 before that and so on, right? But for us before infinity there is finite. There is, for us there is nothing more. So in that way I'll just state, if there are infinitely many pigeons, I don't need to write this, but writing it, okay, and so it becomes more clear. Infinitely many pigeons and finitely many cages, okay, then at least one cage has infinitely many pigeons. Okay. Now just to make a not very useful point again, but this becomes more of like interpreting some theorems as pigeonhole principle. So you will meet some theorems later on which you will prove in a very different way. Okay, but then just to just to find shelter, in the sense that just to make that theorem look not so bizarre, you will try to frame it like a pigeonhole principle thing. You say, okay, so then it's pigeonhole principle type of thing. Okay, that happens. So a lot of results are of this nature. So there was one theorem. I'm just thinking this for myself. Give me a minute. Yeah, okay. I'll not say that, but just for myself. There's something called bare category theorem. So there it's a similar kind of thing, but then there is something like if there are uncountably many pigeons and countably many uh, cages, then one of them goes into countably many, and there's more than that. But for us, there is no anything called uncountable now. So this is a simple. This is what we have, and we'll try to apply this. Okay. Let me begin with an application of this from one of the problems which I had given you guys. Okay, in the sample questions, easy sample questions. Well, this maybe was not. Let's see. So this is problem number 10 from Arthur Angel. So this problem 10. Yeah, problem number 10. Okay. So this says that given 11. So if you are given 11 decimal numbers, okay, so 11 decimal numbers, like, so you'll have 1, 2, 1, 1, like this, and then there are 11 of them. Okay? 11 decimal numbers. Show that there are at least 2, okay, which agree, okay, which agree at infinitely many places. So just to, just once again. What do I mean by agree at infinitely many places? So there will be things like this. Okay. 1, 2, 2, 1, 2, 2, 2, 1, 2, 2, 2, 2, 1, like this kind of number. And then maybe there will be a number like this. So you have to show that there are numbers like this. Now you see these two decimal places are not the same, but they agree at infinitely many places. They keep agreeing. So to think of infinitely many, you can just think that they'll keep agreeing as you go forward. They just keep agreeing. They will not agree everywhere, but they will keep agreeing at some point, and after some, after that point again, at some time in the future, they will agree. Something like this. Okay. And you can see this is very clear that these are agreeing. Maybe I could have given a better example. Yeah, but yeah, some LCM, SCF I could have given. But anyways, like you see, this agrees. And if you follow the pattern, you can see that they keep agreeing, obviously. So you want to show that in 11 decimal expansions, there are 2 of them which are like this, which keep agreeing. So first is a question. Okay. Okay. Right. If it's not clear, then you should tell. So basically, there are 2 sequences which agree at infinitely many places. So there will be 11 decimals. We can forget the part before the decimal. So A1, A2, dot, 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 dot. And then again, I don't know, B1, dot, 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 dot. And again, dot, dot, dot. And there are 11 of this. Okay. So I don't know what's 11th alphabet. I think H or something. Okay. Yeah. Okay. Right. No, I was not thinking of that. But anyways, yeah. So we want to show that 2 of them are such which agree at infinitely many places. This is let's think. This is the easiest example I could find. Okay. Other than some trivial ones, I can just shuffle that statement that we have in beginning and make. But let's try this one. There are 11 of these. That's important. There are 10 possible digits, and there are 11 numbers. No, denominator can be anything, right? The denominator doesn't have to be between 0 to 10 or anything like that, right? Between 0 to 9. Okay, the denominator can be 13 by 57, anything like that. But like, don't think about the denominator. That will take you in a very different direction. Think about this decimal form only. This is just like a list of numbers. Okay, just 11 sequences, and every term in the sequences are from 0 to 9. Okay, that's all. Think, then I will try to make it easier. Let's see if I Yes. So basically, at some place the digits will be the same. So, for example, if you consider this, and then you consider 0, 0, 0, 1, 0. So they are in these two numbers are in agreement at this place. Okay, right. And we want to say that there are two numbers which are in agreement at infinitely many places. Okay, that's so they're in agreement here. Then after maybe some 1 million terms, it's possible they will agree again. A huge number of terms again they'll agree. And what will be the agreement place? That we don't know. What will be the agreeing numbers? That we don't know, but we know that they will agree. That's what we want to show. No, that is not true, if I have understood you correctly. If you take any two numbers, you're saying, or at least two, right? But not at some point. Just even in the first point, even in the first column, you can say that. That's the first step, right? In the first column, there will be two numbers which are same. Okay. So two of these numbers will agree in the right in the first column. Okay. Now try to extend this. Think I'll just maybe I should. Huh. Second column also two numbers will agree, but which two numbers will agree, we don't know. Okay. So first, second, I'm just writing it like this. 11th. So in the first column, two numbers will agree. Which two, I don't know. So maybe it is like the first one is 1 in the first place, first column. And let's say the fifth one is also like this. Okay. So is this clear with everyone? Just 11 numbers, 10 possible digits. So two digits have to be the same in the first column. When you come to the second, yeah. Yeah. Okay. So how do we, so second column also two digits can be same, but then we don't know. It could be that the first one is again involved, but it could be that the second one. So in every column, two digits are going to be, so in every column, two digits will agree. Two digits will be the same. For any place, rather I should say for any decimal place. For any decimal place, at least two numbers will agree. So let's say that for the first decimal place, 1 and 5 are agreeing. So I'm writing it like this. For the second decimal place, 1 and 2 are agreeing. So I'm writing like this. Is this notation okay? I find this crisp. But fine. And in the third, let's say in the third column, you don't know, let's say second and third agree. Second and third numbers agree in the third column. And let's say that, so let's keep a good notation. So in the fourth column, let's say some seventh and eighth, because there are 11 numbers, agree. So far, this is, yeah. Okay. So here I should maybe say that the decimal, no. So I don't have to say that, yeah. Because then it will be 000. Yeah. See, if there are two rational number, okay, if there are two numbers in this whose decimal thing terminates, right? If there are two numbers in this whose decimal expansion terminates, then we are good, right? We can go home, because then after that they are both 000. So they agree. Okay, but we will assume that is no, that is, yeah. But so as Ishana has said here, so I will try to just say that, see, what do we want? Yeah, we want one pair which occurs infinitely many times. Is that right? We want some pair like this pair 1 comma 5. It would be good if this same pair occurs infinitely many times, though that may not happen, but then it will be good, right? Because then the first and the fifth number agrees in infinitely many places, but that may not happen, but that is what we want. So then what do we do? So we want some pair to occur infinitely many times, right? Yes. So you want to say there are infinitely many columns, right? Yeah. So there are infinitely many columns, or if you're writing infinitely many decimal places. So let's write this, because this is the first time we are doing this kind of thing. There are infinitely many decimal places. So these are the pigeons. Okay, but there are infinitely many decimal places. And how many pairs are there? There are, how many possible pairs are there? There are finitely many. We can even just say that it's 11 choose 2 or some 10 choose 2, right? If you know this notation, otherwise, okay, it's not 10 choose, yeah, whatever you can say. Yeah, because the pairs, right? The first part, you can say whatever. The first part can be from 0 to, no, 11 choose 2. The first part can be from 1 to 11, and the second part can also be from 1 to 11. Yeah, so maybe you can say 11 into 10, which is not correct, but 11 into 10 is certainly upper bound. It cannot be more than that. The 11 into 10 pairs. Yeah, at most. Is it fine? Yeah, there are these 11 into 10 pairs. So there are some finite number of pairs. Okay, and there are infinitely many columns. Yeah? So some pair will have to come infinitely many times. Otherwise, how are you going to get infinitely many columns? Yeah, so some pair has to appear infinitely many times, and then we are done. Okay. So is it good? Making sense? No, that's possible. That is possible, but at least one cage. Okay, I should say at least one cage has infinitely many pigeons. Yeah, yeah, but that's not a general truth. It may be false sometimes. Yeah, but what is true always is that one cage will have infinitely many pigeons. Right, like that. That's something we can always say, right? But whether two cages will have infinitely many pigeons, yeah, that can happen, cannot happen. Yeah. Okay. This is a very good fact, right? I mean, this fact was not, it's not obvious immediately, right? That this thing is, I try to rewind and think, right? It just gives you 11 decimal places. They say that, there are two numbers which agree in infinitely many places. It's not immediately obvious, right? I mean, if it is, then it's very good. Yeah. Okay. That's why this is a good yeah, thing. Yeah. So what I learned from here is that we shouldn't get, you know, panicked by infinitely many. You can just analyze it column wise and things like that. Okay. So this is the first problem. Okay. Let's do a second problem. Sometimes actually infinitely many problem is easier. Okay. uh, we will try to see in the next part, because here we had to prove something about infinitely many, and we had infinitely many available, so we had to use infinitely many. But there are some problems in which infinitely many availability makes the problem easier, you can imagine. So the problem is like this. So this is problem 2. Okay. So let me first write this. Every point, every lattice point, I should say, every lattice point is colored either, this is a standard question again, but I'm giving an easier version first. Let's try this. Either red or blue. Okay. So lattice point just means those with integer coordinates, but you can just focus on the upper part, this part that I've drawn. And then there are just lattice points. Okay. So these are the points. Just grid. So there is a grid and every point is going to be colored. I'm not coloring it now. And so on. It goes on and on. Okay. Red or blue. Okay. What we want to show that there is a monochromatic rectangle. There is a monochromatic yeah. So monochromatic rectangle means that the vertices of the rectangle, all four vertices, will be of the same color. Okay. So I'm not coloring it now. Just see, then maybe I can color. So no matter how it is colored, you want to show that there is a monochromatic rectangle. Today I'm feeling very tired, unusually tired. Hmm. Yeah. So one of them could be red, some could be red like this, some could be blue. But you want to show that no matter how this is done, you will have a monochromatic rectangle. Okay, here you can already find one. That blue rectangle is popping up. So, yeah. So maybe to avoid that, I can try to make this red. Yeah, that's what we want to show. But how do we show it? So there will be infinitely many red or infinitely many blue points. But yeah, how do we use that to show that they form a rectangle? Okay, in a row. So let's look at the 0th row, R0. No, row 0. So you are saying that there will be row 0. So there will be one color which will come 2 times or infinitely many times. At least twice, and you can say infinitely many times, but yeah. So at least some color comes at least twice. Yeah. So we can just say that assume that red appears at least twice. When it appears, we don't know, but let's say this. Well, I will actually go and say, I'll say that it is in at least infinitely many times. Yeah, infinitely many times. Because why not? We have infinitely many. Mm-hmm. Right. So for the first column, also we can say that there will be at least two red, there will be infinitely many reds or infinitely many blues. Two pairs of points, yeah, same level. So what does that mean? Above the point. Um, yes. Okay, y coordinate will be the same. Yeah. So on the same, so like in this level, there are two reds, but then, so what can we say about the level above? First level. So in the first level, you see, it could happen that these two are blue, right? Or it could be red, blue, right? You cannot yet say. Two rows. Uh-huh. So you're saying that there is another row which agrees with, uh, there are two rows which agree in infinitely many places. Yeah. So why are there two rows which agree at infinitely many places? Yes. Yes. Yeah. So we can basically say from the last one only that there are two. Well, you could say it in terms of columns or rows. Let me just say it in terms of columns. Yeah. So basically, you see, if you look at the first column, okay, then there will be two. There will be in the first column there will be two rows which will repeat. Yeah. You do not really need so many rows. You can just take three rows basically. Yeah. If you even just take three rows, right, then there will be two rows, two items in this column which will have the same color. Okay. Then you go to the second column, and again, you know, again, but no, no, no. No, in that sense, there are two colors. Yeah. And no, but there are infinitely many rows. That's actually better. That's not a problem, right? That's even better. Yeah. No. So what I was saying is that like this is the first. Yeah, first row that agrees. But then the problem is that why should why should there be another column in which you have two blues in the same place? Yeah. So, I mean, so we get that this, so just to say it, here we get that these two agree, right? Okay. Now it, now if you go to the second column, then there will be like this, these two reds agree in the second column. Yeah. If you go to the third column, then it could be that these two, first and the third row agree. Okay. Uh, but you can see that there will be two rows which will agree at infinitely many places. Just like that's just the previous problem. Right? Yeah. Because because there are only three rows, right? So there are uh, three choose two pairs, right? So here we, maybe I can say this is third and second, right? So third and second are agreeing, and here maybe I can say second and first are agreeing, and here I can say third and first are agreeing. Yeah. So basically there will be two rows which occur at infinitely many places. Okay. So let's say that this row and let's just say that these two rows, yeah, these two rows occur at infinitely many places. Okay. What does that mean? It doesn't mean that they occur everywhere. So it doesn't mean that they agree everywhere. Okay, it could be that it is like this, and then if you go to the next one, they may still not agree, but they will agree at some point later. Okay, there will be some point in the future where they will again agree. Okay, and then again they will agree, and so on. Is that okay? Okay, but then how do we get a rectangle? It is simple, but uh, no. So no. So if to say something more, yes, right. So like these two, you're getting these two blues, but it doesn't mean that you'll get two blues again, right? You're getting two reds here. It doesn't mean that you will get two reds again, right? But you will get two blues or two reds once again, right? Because they agree again at some point in the future, right? They agree again here. So yeah, because there are only two options, either both are blue or both are red, right? So they will be both, they will be, yeah, the reds will come again or the blues will come again. Is that okay? We need to say this. Yeah, there's slightly more that we need to say, because just this row which agrees at infinitely many places, just the places that they agree in are not enough. Because see, they agree in the first column and they agree in this column, but we can't use these two because two of them are blue and two of them are red. So is it kind of? Yes. Yeah. Yeah. We are applying it twice. Yeah. That again, these pairs these agreeing values, this could be 1, 1, 2, 2, 3, 3, but that 1, 1 again has to come. And okay, at least one of them has to come again. Red, red has to come. The red, red thing has to come infinite again, or the blue, blue thing has to come again. Is that, yeah? Then you get a monochromatic rectangle. So is it okay? Because there are infinitely many places in these two rows. So we only need to now think about these two rows. Is that okay? Right? So why are we thinking about these two rows? Because we have found two rows which agree in infinitely many places, right? And then only focusing on these two rows, we will get that same color of agreement. That same color will come once again somewhere at some point. Yeah, is it okay? Okay. So Aparna, is it okay to you? Oh, good. Okay, nice. So this way we actually have a generalization of the previous problem, right? Not just there will be two decimal places which will agree infinitely many times, but you can even say that the values that they agree on, that will also, so there will be some value like 5, okay, such that they will agree at 5 infinitely many times. Again at 5. Okay, because again, right, there are only 9 digits, right? And so one of those, because they're agreeing at infinitely many times, some digit has to occur infinitely many times. Right? So there will be two numbers which agree at infinitely many places with the same value. Okay. So that is, but the way we have done this question, I this is not a very good way to do this, okay? Because it seems like you will need infinitely many columns. Yeah. Do you guys agree? The way I have done this, it makes it seem like you will need infinitely many columns. Yeah, because I could have this red, blue, blue, red, blue, blue, red. I could continue like this. Or so, or not, but yeah, in this 2 rows, if I restrict, then I can continue. But that is not good, right? It seems like I need infinitely many. But so here is the thing, that you don't need infinitely many. That's a harder problem. So you guys can try it. So I don't myself, I don't know the exact number which will be needed to always guarantee a monochromatic. I could find it, but I'm not, take some time. So let me not think now. I'll just give you a number which I know will work, kind of big enough number will work. So if I give you a 40 by 40 grid and it is colored with red or blue, then you find a monochromatic rectangle in that. Okay. So you guys think I we shouldn't. I mean, I can now give a try to guide, go in a different alternate solution from where you will realize this. But you guys can think of it on your own first. Okay. That if you have a 40 by 40 grid, should find a monochromatic rectangle. Okay. Think about this. Yeah, so you can just note this down and erase this. So let's go to the next problem. Feeling extremely tired today. So the next question can. So again, I want to do a problem which is of this type. This infinite type. Let's do an interesting problem. Okay. It's slightly different in nature. I doubt if you'll find this in Arthur Angel. It's a slightly funny, different problem. Yeah, let us say that you have a machine. Okay. But if I give you the machine, then it's very simple. Anyways, yeah, let's say that you have a machine. So this is a machine that takes in like a word and it accepts it or rejects it. So this is where the word kind of enters. Okay, so let's say that for simplicity, okay, for simplicity, let's assume that these two are only only alphabets, or these are only digits we have, and the words will be just strings. Yeah, just like this sequence, you can say. Yeah, but so, yeah, you're not allowed to. So you can take any length, big length. Okay. So this is these are the words. So these are the strings. They will enter into this machine. So let's say this enters. Okay. Then if I see what the machine does. So if I'll explain this. And this is final. Okay. So what this machine does is when this word comes in, it will read from right to left, naturally from right to left. So when at this stage it scans this 0. Yeah, this is the first input. 0 goes in. Now the arrow will tell you where this will go. Okay, to what other state it will go. So since I've seen a 0, my state will come here. Okay, and now this will be the input because the first input is eaten up, right? It's done. Now again it sees a 0, so then this is done, and I will move here because you can see the arrow tells you to go there. Now I kind of have 1 1. So now I see a 1, so I will come here to the final state. Now again a 1 is left. Okay, so maybe I should just say no. So let me not say anything. So again a 1 is left, but then that 1, nothing can be done. That 1 will remain. It gets stuck. Yeah, so the entire word is not accepted, right? Yeah, when you reading the word from right to left and you're moving on the graph, as it tells you, then you are not accepting the entire word, right? And you're reaching the final stage. Okay, so this word we say is not accepted. Yeah, let me give you another example. Will be more clear, hopefully. So, Hare Baba. So I don't know if this will be very hard or easy, but just trying because it's a new thing. Let's take another example. Let me think of an example that will work. So let's take 1, 0, 1, 0. Okay. So what will happen to this word? Can anybody say? So let me also mark like state A, B, C, and this F. So because of the rightmost one, where do we go? We go to state B. Is it fine? Yeah. When this word is read, we go to state B. Now, when you read the word, or rather the letter or the digit, when you read we use it in that way. So if you read the digit 0, then you go to F. Okay. Now, when you read the digit 1, the arrow tells you to go back to state B. Okay. Again, when you read 0, you go to the final state or the accepting state. Accept. Okay. So you see what happened in this? The entire word was read. Okay. The entire word was read and you ended up in the final state, accepted state. After the entire word was read, the last letter when it was read, you went to the final state. So this way we say that this word is, or this number is accepted. So is it clear, like what does it mean to say that a number is accepted? Sorry. No, after reading this 0, it goes to F, right? And so it has reached the final stage when the word is read completely. Yeah, let's take another word. Let's just extend this a little bit. Let's take that, then also it will be more clear. If there is one more 0, now there is one more 0. Okay, so now what happens? Someone tell me, so what happens when you read this word? Yeah, goes to B. So then at B, it has to read 0, right? So it goes to F, right? Okay. Then it reads a 1. So it again goes to B. You can see from F, when you read a 1, you go to B. That's the rule. Okay, now you're at B and you're reading a 0. So you again go to F. But now at F, you cannot read a 0. That's not in our machine, right? At F, 0 lane, if you take in 0, then where do you go? Nowhere, you're stuck. So it cannot be read. There is an error it will throw up. This word I cannot read. You see, this cannot be read because I have not told you what happens when at F you read a 0. Where do you go? Nothing is said. So it's an incomplete thing. So this cannot be accepted. Okay, let me give you another variation. This is a fantastic thing actually, in a sense. Let's see this word. Okay, what happens when you finish this word? You are at B. Why? Because first you go to B by the 1, then you have a 0, so you go to F, then you have a 1, you go back to B. But then you are at B. After you finish reading the word, so you have completely read the word. In this case, there was not that kind of error was not there. You completely read the word, but you didn't end up in the final state. So this is also not accepted because you're not ending up in the accepted state. Okay, so this is the meaning of what it means to say that some word can be accepted and some word cannot be accepted. Okay, this is called an automata. Okay, it's very useful, and yeah, let's save that for now. Okay, so Nagesh, have you seen this thing earlier? Entire semester, right? Yeah, fourth, yeah, some. So you would have seen this. Okay, but my question is very pigeonhole principle we want to think of. So can you show that this machine accepts infinitely many words? This is not even going to need pigeonhole principle, but yeah, show, and I don't want you to find all the words or describe all the words. That can also be done, but that's not the goal. Show that uh, this machine accepts infinitely many words. So we also had this course on automata theory long time back. Then last semester, I not last semester, I took one course. It was algebraic automata theory. So that was studying automata theory using mathematics. Okay, yeah, using no computer science, all the theory of semi groups and so on. Very interesting. But let's think about this. So like we already had an example, right? So we had 1, 0, 1, 0. Yeah, this was accepted, right? Because 1, go to B, go to 0, go to F, go to 1, go to B. So you are at A, you read a 1, you go to B, then you read a 0, you go to F, read a 1, you go to B, and read a 0, back to Final state, word is read completely and you're also at the final state. Good, accepted. Can you use this to build more words which will be accepted? Exactly, right. So, right. So you can just add another 0, 1. There's nothing else to do. No, 1, 0 or whatever. Yeah, same thing. This, and so this is like a trivial question. This is nothing. And then you can, words like these will be accepted. And certainly there are infinitely many of them. And there are others also, like there is the 0, 1, which is also accepted. Yeah, this. And there are others, but that's not the point. We have produced infinitely many. That's our goal. That's enough. Okay. This was not pigeonhole principle. I want to get you guys a little comfortable with this before asking that. So this is fine. Okay. So now if I now, I will not describe the machine now completely. I will just say that there is a machine with, let's say, so see this, we basically gave an infinite family of words, right? Kind of but we want to say that sometimes you can show that machines accept infinitely many words without having any idea of what those infinitely many words are. Okay, so let's say this is the final stage and these are things, some arrows are there and let me not describe them, it's not useful. Okay, some arrows, some other arrows. Okay, this is the initial state. Okay, what I want to ask is, if this machine, this will be a little difficult, so I don't expect that you'll be able to do it, but I just want to say it and you will kind of, it's very, very interesting. This is just a little bit extra. Okay, this is not, well, let's see. If this machine accepts a word of, so obviously again we have only zeros and ones. Let's say if it accepts a word of length 1000. Okay, just one word of length 1000, if it accepts, at least if we know at least that, then it accepts infinitely many words. So again, some sort of cyclicity we have to show, right? There was a cyclicity which was exploited last time, right? But here it will be more indirect. Okay, so this question becomes very easy if you're made more comfortable in this topic, but that we don't have time for that. Then we'll go in a different thing. But it's a fair enough commentaries question. No, that is already given. Yeah, if this, so you assume that this accepts a word of length at least 1000. Okay, then it will accept infinitely many words. Okay. So again, the point here is that if you have a big enough word, then you will have some sort of a pattern in that word, and that pattern can be repeated again and again. Okay, that is the thing. No, but then that's, it's not necessary that that will be accepted, right? See, if you just take any word and you double it, then that's not necessary that that will again be accepted. You see, that happened luckily the last time, but it doesn't always happen, right? Because there was something there which doesn't always happen, right? That you can, well, it can be said when it happens, but yeah, even last time not all words could have been doubled, you know. So that particular thing was kind of, yeah, but not everything can be doubled. So yeah, Well, let's see. I mean, if you assume that it's like simple, so there are 1, 2, 3, 4, 5, 6, 7. Yeah, there are um, seven vertices, 7 points, 7 vertices, right? If there is a word of length 1,000 which gets accepted, then it just imagine, right? So there was a, I mean, it's all zeros and ones only, right? Nothing more complicated. In that doesn't matter if you could make it, but some word of length 1,000, some big word of length 1,000. Okay. Now just imagine, yeah, this word entered and it kind of traveled, right? It traveled inside something, something, yeah, then it finally went. So don't you agree that it would have gone in some sort of a cycle at some point? Ah, that is the key. That's everything here. Yeah, it would have gone into a cycle. I'm not proving that rigorously, okay, but you can kind of understand that. Yeah, it has to go into a cycle, okay, and a proper directed cycle, like respecting the directions only, because it cannot move contrary to the directions. So it must have gone into a cycle. Even if there is a double edge or something, okay, they won't be like this. Yeah, like 0, 1. It doesn't matter. It will have to go through a cycle because there are so much length it has. Now let's just, catch that going into a cycle. We don't need most of the problem here. We just need the fact that it goes into a cycle. Well, it means that there is a cycle in the word itself, in the automata itself, right? In the machine itself, there is a cycle. Right? Let's say, yeah, just from this one cycle, you can you can repeat that part of the word which uses a cycle. You understand it, yeah. But just to be clear, let's say that, so this is 0 again, not very good, but let us say that this is 0 and this is 1 and this is 1. Okay, so this word would have that 0, 1, 1 in it, right? Because it traveled through this cycle. Yeah, so like whatever this word is, it goes big word, but at some point it has this thing, 0, 1, 1. Okay, this 0, 1, 1. Okay, and you see there was a certain stage in which it read this 0. Some other words were read earlier, some other part was read earlier, but it was in this stage. It read 0, came to this stage. It read 1, came to this stage. It read 1 again, it came to this stage. Okay, now for the rest of the word, it only matters that it is at this stage. That is important. Yeah, for the rest of the word, they don't care about what was read earlier. All they care about is that you are at this pink stage. When starting to read the rest of the word, you are at this pink stage. You read the rest of the word, you go home to the accepted stage. The rest of the word. The rest of the word only cares about what stage it was when that rest of the word was starting to get accepted, starting to be read. They only care about that pink stage. It's a memoryless model of computation. Okay. So this 0, 1, 1 doesn't really matter. All that matters is that you end up in that stage and you read that rest of the word. Well, what does that mean? It means that I can duplicate this part. Yeah, and you guys already see it maybe, but I'm just saying it clear. Yeah, this part, I can duplicate this part because I know I'll again end up in the same ping stage. And rest I will keep. This rest should keep the same. I can't take risk with that. But this part I can duplicate and I can triple it 4 times. And that way I'll get infinitely many words. Okay. That is the thing. See, this is very, I find this very interesting, right? Because you don't know what that word is. And we just took an example, but we don't know what that word is. And but you are able to. Yeah. Yeah. Bigger length is always better. And you don't even need 1,000, right? You just need how many vertices are there? You need one more than that. Then you will get a cycle. You see, that's good enough, everybody, right? If there is 1, 2, 3, 4, 5, 6, you just need 7 length. Why I took 1,000? Because I was thinking something stupid. As per I had some other complicated unnecessarily as usually because I was not confident about it. I was trying to recall something, and I thought that I will need some product of things, but as well, very just you take 7. I feel this is correct. Then you will get a cycle. You can also get a loop. It's not a problem. Well, if you have a loop, then whatever letter is there, you just repeat that letter, right? Then it's good. Right? Okay, this is a 0 or 1, whatever. Okay. This is a theorem in a formal way. This is called the pumping lemma. If you guys want, you can see this. You will find some. If you can't read, if you don't want to read, for some video, they will explain this in a cartoonish way. It will be fun. You can see. Obviously, but for the most serious stuff, you will have to read later. But don't think about that. It's a very powerful result. Okay, so yeah, it's pumping because we are kind of pumping that part, right? With more and more. So it's called pumping lemma. Very interesting thing. It may not, so all of what I've said may not be completely accurate in the sense I've said some non-optimized things, but these are true. Okay. Yeah. So I think let's then stop today. Okay. So well, I was expecting that you guys would ask me more questions, but no problem. We learned this thing. Okay. So from Monday, we will go into a new strategy. Okay. That strategy will be invariance. Okay. We will try to have some process, something happening, some simple thing happening, and in a random way, not much will be known, and we will try to show what cannot be done, what cannot be reached, and so that kind of, maybe I will send some few problems that you guys can try from before. Okay, some like just very common sense questions, and yeah, I'll see. But this is the thing, I've given you guys a reference. So challenges and thrills are maybe number one reference you can consider. Brualdi is very good reference. It's more, Brualdi is more theoretical. Challenges and thrills are standard, slightly challenging and standard. And mathematical circles, if you're looking for non-standard problems, which don't need much theory, which can be, all problems would be just puzzle type, but they can be hard, but they'll be non-standard. That's the nature of that book, as far as I can understand. So these three references are broadly, I think, enough. Arthur Angel, as I said, the harder problem, the actual problems are hard, solutions are given. You can try it, but I suggest don't try it now. You already have three references. You can two at least. Brualdi has more theoretical. Last class we did some of that, but yeah, no, we did easier versions of what is there in that. But anyways, so that's it for today. Okay, we'll meet on Monday with the